Hello everyone, I am Kashish Patel and I am thrilled to have this opportunity to walk you through a fascinating concept in the field of deep learning, which is Gated Recurrent Units, which is also known as GRU. So, GRU are a specialized type of neural network unit designed to process sequential data such as text, speech, and time series. They are known for their efficiency, performance, and ability to solve key challenges faced by traditional models. Today, we will explore GRUs in detail, how they work, why they were introduced, what problems they solve, and how they are applied in real world AI systems. Let's begin our journey into the world of GRU. Before we get into GRU, it's important to understand the foundation they are built on, recurrent neural network or RNN. Unlike traditional feed forward networks, RNN are designed to handle sequential data, where the order of information matters. This could be a sentence, a sound wave, or stock market trends. RNN work by maintaining a hidden state, a kind of short-term memory that summarizes all previous inputs. This hidden state is updated at every timestamp and helps the network make context-aware predictions. Because of this, RNNs are useful in applications like language modeling, machine translation, and speech recognition, where understanding what came before is critical to predicting what comes next. However, despite these advantages, RNN face some serious limitation, particularly when it comes to learning from long sequences. One of the biggest challenges that RNN face is vanishing gradient problem. During training, especially through backpropagation, we use gradients to update the weights of the network. But in RNN, as the number of time steps increases, these gradients start to shrink exponentially. This means the early time step information contributes almost nothing to learn, making it hard for the network to remember things from the distant past. Imagine trying to recall the beginning of a conversation after hearing 100 sentences. It becomes fuzzy. This is exactly what happens to RNN. As a result, RNN perform poorly when the task depends on the long-term context. This serious limitation lead to the invention of improved architecture like GRU and LSTM. To address the vanishing gradient problem, researchers introduced gated recurrent units or GRU. GRU are a variant of RNN that include gating mechanism which act like switches to control how much past information is remembered and how much is forgotten. The GRU cell consists of two key gates, the update gate and the reset gate. So let's talk about the update gate. This gate decides how much of the previous hidden state should be carried forward into the current state. If it's high, more past information is retained. And the second one is the reset gate. This gate decides how much of the past should be forgotten. If it's low, the past hidden state is mostly ignored and the model focuses on the new input. These gates give GRU the power to model both short-term and long-term dependencies effectively. Compared to other models like LSTM, GRU are simple, fast, and often just as powerful. Let's take a closer look at how GRU work mathematically. The beauty of GRU lies in their gated structure. Each gate is controlled by a sigmoid function which outputs values between 0 and 1, especially acting as a filter. First, the update gate denoted as ZT determines how much of the past hidden state to keep its calculated as you can see on the screen the equation. The next is the reset gate which is denoted as RT, which decide how much past information to forget. Using the reset gate, we compute the candidate hidden state And finally, we compute the new hidden state. This formula is especially a blended mix of the past and the present, adjusted by the update gate. It allows the network to decide what to keep and what to change, enabling efficient and flexible learning across sequences. Let's talk about several advantages of GRU addressing RNN limitations. So, GRU have several advantages over both traditional RNN and LSTM. First, they offer faster training. GRU are simple and have few parameters than LSTM, which makes them computationally efficient. Second, they provide better long-term memory thanks to the gating mechanism. GRU handle dependencies across longer sequence more effectively than vanilla RNN. Third, their reduced complexity makes them ideal for environments where memory or processing power is limited, like mobile or embedded systems. And finally, despite their simplicity, GRU perform on par with or better than LSTM in many real-world applications, especially where training data is limited. These strengths make GRU a popular choice for developers and researchers alike. So, let's talk about application and example of GRU. So, GRU aren't just theoretical, they are actively used across many domains. Let's look at some key applications. In natural language processing (NLP), GRUs power machine translation engines, generate text, analyze sentiment, and more. Their memory capabilities help capture the flow of language effectively. In speech recognition, GRU convert audio waves into text by understanding how sound changes over time. Their ability to handle sequence makes them ideal for this task. In time series prediction, like forecasting, stock price, weather, or energy usage, GRU learn historical trends and predict future values accurately. And in reinforcement learning, GRU help agents remember previous state and actions to make better decisions in dynamic environment. Clearly, GRU are not just academic, they are powerful tool shaping modern AI systems. So, in conclusion part, I am going to talk about future trends and further exploration in GRU. So, GRUs have emerged as a powerful tool in deep learning, especially for handling sequential data. They offer a balanced mix, simplicity, efficiency, and performance, while overcoming many of the limitations of traditional RNN and LSTM also. So, let's recap the key takeaways. GRU mitigate the vanishing gradient problem. They provide strong long-term memory. They are easy to implement and fast to train. Looking ahead, GRU are being combined with attention mechanism and are playing roles in transform-based models and multimodal learning systems. If you want to explore more, I encourage you to try implementing GRUs in frameworks like TensorFlow or PyTorch, and even combine them like other techniques for advanced use cases. Thank you so much for your attention. I would be happy to answer any questions.